Troubleshooting motor starter tripping issues can be complex, but a systematic approach can help identify the root cause. Here are several potential causes and troubleshooting steps to consider. Firstly, it's crucial to verify the overload heater selection. Ensure that the overload heaters used are correctly matched to the motor's nameplate current rating. Oversized heaters might be tripping prematurely, so double-check the specifications. Reconfirm that the overload heaters used match the motor nameplate current. Secondly, inspect the contacts within the starter for any mechanical binding or sticking. This can cause them to trip when opened. Open and close the starters several times to check for any binding or sticking of the contacts. Thirdly, inspect the wiring and connections to the starter and motor. Look for any loose or damaged components that could be causing arcing or voltage surges. Ensure that all wire connections are tight and properly made. Use a multimeter to check for continuity and any loose connections. Fourthly, check for any voltage transients or spikes in the power line during shutdown. These transients can cause the starters to trip. Use a voltage monitoring device to capture any voltage spikes during shutdown. Fifthly, contact the starter manufacturer to inquire about any known manufacturing issues or recalls that may apply to the specific model. If the above steps do not resolve the issue, contact the starter manufacturer for support and troubleshooting assistance. Let's delve deeper into each of these potential causes and solutions. Overload heaters are designed to protect motors from overheating due to excessive current. They are selected based on the motor's full load amperage, which is listed on the motor's nameplate. If the overload heaters are too large, they won't trip quickly enough to protect the motor, but if they are too small, they will trip prematurely. To verify the heater selection, consult the motor's nameplate for the full load amperage. Then, refer to the starter manufacturer's data to determine the correct heater size for that amperage. It's essential to use the manufacturer's data because different manufacturers use different heater curves. Mechanical sticking within the starter can prevent the contacts from opening and closing smoothly. This can cause the starter to trip, especially when it's turned off. Inspect the contacts for any signs of corrosion, dirt, or damage. Clean the contacts with a contact cleaner and lubricate them with a silicone-based lubricant. If the contacts are severely damaged, they may need to be replaced. Electrical faults in the wiring or connections can also cause the starter to trip. Loose connections can create resistance, which generates heat and can damage the wiring. Damaged insulation can expose bare wires, which can cause arcing and short circuits. Use a multimeter to check the continuity of the wiring and connections. Look for any loose connections or signs of damage. Tighten any loose connections and replace any damaged wiring. Voltage transients or spikes in the power line can also cause the starter to trip. These transients can be caused by a variety of factors, such as lightning strikes, switching surges, and the operation of other electrical equipment. Use a voltage monitoring device to capture any voltage spikes during shutdown. If you find that voltage transients are causing the starter to trip, you can install a surge suppressor to protect the starter. Manufacturing defects are rare, but they can occur. If you've tried all of the other troubleshooting steps and the starter is still tripping, it's possible that there's a manufacturing defect. Contact the starter manufacturer to inquire about any known issues or recalls. In addition to these troubleshooting steps, there are also some preventive measures that you can take to reduce the likelihood of motor starter tripping. Firstly, use high-quality, name-brand starters from reputable manufacturers. These starters are typically more reliable and durable than cheaper starters. Secondly, consider using soft starters to reduce voltage transients during motor shutdown. Soft starters gradually increase the voltage to the motor, which reduces the inrush current and minimizes voltage transients. Thirdly, implement a preventative maintenance program to regularly inspect and clean starters and contacts. This will help to identify and correct any potential problems before they cause the starter to trip. Also, note that some starters have a trip-free mechanism that prevents resetting until the overload condition is cleared. When performing any electrical work, always follow safe work practices. To energize the circuit before working on any electrical equipment, Wear appropriate personal protective equipment, such as safety glasses and gloves. If you're not comfortable working with electricity, contact a qualified electrician. Remember to always consult the relevant electrical codes and standards, such as the National Electrical Code, or NEC, for guidance on electrical installations and safety requirements. For instance, NEC Section 430 covers the requirements for motor circuits, including overload protection. NEC Table 430.52 provides guidance on selecting the appropriate size of overload protection devices for motors. NEC Article 430 provides comprehensive requirements for motors, motor circuits, and motor controllers. This includes conductor sizing, overload protection, short circuit protection, and disconnecting means. Proper selection and installation of these components are crucial for ensuring the safe and reliable operation of motor systems. NEC Section 430.22 specifies the minimum conductor ampacity for motor branch circuits. The conductors must have an ampacity not less than 125% of the motor's full load current rating. This ensures that the conductors can handle the motor's normal operating current without overheating. NEC Section 430.32 covers overload protection for motors. Overload protection devices, such as overload relays or fuses, are designed to protect the motor from overheating due to excessive current. The overload protection device must be sized appropriately for the motor's full load current rating. NEC Section 430.52 provides tables for determining the maximum rating or setting of motor branch circuit, short circuit, and ground fault protective devices. These devices, such as circuit breakers or fuses, are designed to protect the motor circuit from short circuits and ground faults. The size of the protective device must be carefully selected to coordinate with the motor's starting current and the conductor ampacity. NEC Section 430.110 covers disconnecting means for motors. A disconnecting means, such as a switch or circuit breaker, is required to disconnect the motor from the power supply for maintenance or repair. The disconnecting means must be readily accessible and capable of interrupting the motor's full load current. When dealing with three-phase motors, it's important to understand the different wiring configurations, such as delta and Y connections. The voltage and current relationships in these configurations differ, and it's essential to consider these differences when selecting motor starters and overload protection devices. For example, in a delta-connected motor, the line voltage is equal to the motor's rated voltage, but the line current is 1.732 times the motor's phase current. In a Y-connected motor, the line voltage is 1.732 times the motor's phase voltage, but the line current is equal to the motor's phase current. These relationships affect the selection of overload heaters and the sizing of conductors. Consider the impact of harmonic currents on motor starters and overload protection. Harmonic currents are non-sinusoidal currents that can be generated by electronic devices such as variable frequency drives or VFD. These currents can cause overheating and premature failure of electrical equipment, including motor starters and overload relays. If harmonic currents are present in the system, it may be necessary to use harmonic filters or specially designed overload relays that are less sensitive to harmonics. Also, consider the ambient temperature when selecting overload heaters. Overload heaters are typically calibrated for a specific ambient temperature, such as 40 degrees Celsius or 104 degrees Fahrenheit. If the ambient temperature is significantly different from the calibration temperature, the overload heater's tripping characteristics may be affected. In high-temperature environments, it may be necessary to use overload heaters with a higher current rating to compensate for the increased ambient temperature. In low-temperature environments, it may be necessary to use overload heaters with a lower current rating. In addition to the troubleshooting steps mentioned earlier, it's also important to check the motor's nameplate data for any specific recommendations or requirements. Some motors may have special overload protection requirements or limitations on the type of starter that can be used. For example, some motors may require the use of a specific type of overload relay or a specific starting method. It's important to follow the motor manufacturer's recommendations to ensure proper motor protection and reliable operation. If the motor is connected to a variable frequency drive or VFD, it's important to coordinate the VFD overload protection settings with the motor starter's overload protection. The VFD typically provides its own overload protection, but it's important to ensure that the VFD settings are coordinated with the motor starter's overload relay to prevent nuisance tripping or inadequate motor protection. The VFD manufacturer's instruction should be consulted for guidance on coordinating the overload protection settings. When replacing a motor starter, it's important to select a starter with the same voltage, current, and horsepower rating as the original starter. It's also important to ensure that the new starter is compatible with the existing wiring and control system. If the new starter has different wiring or control requirements, it may be necessary to modify the wiring or control system. It's also a good practice to upgrade to a more modern starter with advanced features such as electronic overload protection or communication capabilities. When troubleshooting motor starter tripping issues, it's important to have a good understanding of the motor's operating characteristics and the characteristics of the electrical system. This includes understanding the motor's starting current, running current, and overload capacity. It also includes understanding the voltage and current levels in the electrical system, as well as the presence of any harmonic currents or voltage transients. A thorough understanding of these factors can help to narrow down the potential causes of the tripping issue and identify the most effective solutions. Motor starters are critical components in motor control systems, and their proper operation is essential for ensuring the reliable operation of motors and the equipment they drive. By following a systematic troubleshooting approach and implementing preventive maintenance measures, you can minimize the likelihood of motor starter tripping issues and keep your motor-driven equipment running smoothly. If the problem persists after checking all these points, a deeper analysis might be needed involving specialized tools for power quality analysis or vibration analysis if the motor is suspected of having mechanical issues contributing to the electrical overload. Remember to always prioritize safety and consult with qualified professionals when dealing with electrical systems. This narration offers a comprehensive guide to diagnosing and resolving motor starter tripping issues. Remember that safety should always be the top priority when working with electrical equipment. If you are not comfortable working with electricity, it is best to consult a qualified electrician.